Hello and welcome to this video for Chapter 5 of Basic Sentential Logic, Informal Fallacies and Cognitive Biases. In this video, I'll be talking about material corresponding to Section 5.7 of the text, and the topic is the fallacy of false cause. This is the last fallacy. It's also the most involved one, so this video might be a little longer than some of the others. Let's start with a quick definition of the fallacy. A fallacy is committed when one concludes that A causes B, when in fact all that's been shown, or the main premise, is a correlation between A and B. Before I leave this slide, a few things I want to talk about. A and B could be anything. They could be objects, they could be events, it could be a certain kind of food causes cancer, it could be a certain kind of putting one of our players on the court causes us to lose the game. It could be electing a certain political party results in a certain kind of economic benefit or mishap. So it could be a type of thing. It could be even just one thing. It could be something like, oh, that chicken I ate made me sick. Okay. But the key is that the conclusion is about a causal relation. Something is causing something else, whether it's one thing or a type of thing is causing some other type of thing. What's a correlation? A correlation is just pointing out that two things occurred together. And I'll talk more about some correlations, how those get expressed in a minute. But it's either something like whenever A happens, B happens. Whenever you see a lot of A's, there's always a lot of B's. And when there's no A's, there's no B's. Things like that. These things tend to either be present together or to be absent together. That's a correlation. I'll talk more about that in a minute. But first, let's see some examples. During the past 2 months, every time the cheerleaders have worn blue ribbons, the basketball team has won. So there's your correlation. You have two types of events. The cheerleaders wearing blue ribbons. And it's a type of event. It's not one specific event, because this isn't like, oh, on Thursday they wore blue ribbons and on Thursday our team won. That would just be one particular event. Now you could have an argument like that and maybe false cause argument based on that. But in this case, the one we're looking at here, it's a type of event. The cheerleaders wearing blue ribbons, and the claim is that's correlated to another type of event, the basketball team winning. So that's the correlation. They then go on to conclude that there's a causal connection. So if we want to keep winning, they'd better continue to wear the blue ribbons. Notice that the word causation doesn't show up here. Now, sometimes when people are making a causal claim, they'll use the word cause. But not always. And in fact, I think most of the time they don't. What they will do is they will imply some kind of control. So they'll imply that you can control B by controlling A. We can control whether the basketball team wins by controlling the color of the ribbons. That's how you know that the claim is really a causal claim. Let's look at another example. Children become able to solve complex problems, predict the behavior of others, and think of objects objectively at the same time they learn language. Therefore, learning a language is what causes these abilities. So again, you can see here, there's a whole lot of correlations being mentioned. And the correlations are, let's just say, correct. So the issue with false cause fallacy isn't that the correlations are wrong, that the person is wrong about the correlations. What makes something a false cause fallacy is something else. It's the move from correlation to causation. And all we have here is correlation. And here we do have this explicitly, it's saying that there's a causal connection. Let's do one more example. Every time Marshawn Lynch carries more than 30 times, the Seahawks win. So this is football. Marshawn Lynch, football player. and he's a running back. So how many times does the team give him the ball to run it? And there's a correlation here. Whenever a certain type of event happens, he runs the ball more than 30 times. Another kind of event happens. His team wins. Now we're going to see the causal claim. So Al Carroll, the head coach, by the way, a lot of this is outdated. So all Carroll has to do to keep the Seahawks winning is to give the ball to Lynch at least 30 times a game. So we know it's a causal connection because the person writing this passage is claiming that one can control whether the Seahawks win by controlling the number of times that player carries the ball. So the form of the most basic version of a false cause fallacy, towards the end I'll talk about slightly less basic versions, but the most basic version, and most of the time what you see is this. Premise: A and B are correlated, therefore 2A caused B. Okay. Now, how can the correlation premise be expressed? Rarely will people use the word correlated. What will they say, or what are the kinds of premises that get used in the real world? Well, it'll be something like A happened, then B happened. I ate lunch at Taco Bell, then I got sick. By the way, I don't want to dump on Taco Bell. Taco Bell's great. I've eaten there many times, especially in my younger years. But whatever. It could just be one event. A happened, then B happened. It could be a whole bunch of events of various types. Every time A happens, B happens. Every time we elect a president from political party X, then we have an economic crisis. Okay? Whenever A happens a lot, then B happens. So these are ways that a correlation can be expressed. What about the causal claim? Sometimes the person might just use the word caused. A caused B. Usually it's in terms of control, though. If we want B, we should implement A. So I'll say, every time we've elected a president from Party X, the economy booms. So if we want a booming economy, we should elect someone from Party X. Okay? If we don't want B, then we should prevent A. Right? So if I say every time we elect someone from Party X, we have a recession. If we don't want a recession, we should not elect Party X. Right? So that's usually how these things are expressed. So for example, the football example, by the way, is, even though I made it up because it was in general, I've heard this kind of thing by sports commentators all the time. Here's an example of someone actually making this exact fallacy. In the case of football. In the news conference after the loss to the Cowboys, Sean McVay, so that's the opposing coach of this game, the coach who lost, said he needs to find a formula that would allow the Rams to win consistently. So the head coach of the team that just lost the game is saying, well, I need to figure out a way for my team to win consistently. Now the sports commentator says, well, here it is. Here's your formula. Todd Gurley has to carry the ball at least 17 times a game. Over the last 2 seasons, when Gurley gets 17 carries or more, the Rams are undefeated. So the premise is a correlation. We've got the last 2 seasons, and every time this player has carried more than 17 times, the team has won. And so this commentator is saying that, well, here's the formula for making sure your team wins. You can control, head coach, whether your team wins in this pretty easy way. Give this player the ball at least 17 times a game. So every time A happens, B happens. That's the premise. So if we want B, if we want to win, then we should implement A. We should give that player the ball 17 times. Okay? So that's the form of the fallacy. That's how it looks like, what it looks like. But now I want to dig deeper into this thing. And I want to dig deeper by asking the following question. Now, there's an answer to the question, but I first want to pose it in a way that hopefully will make you think a little bit. The question is science based on false cause fallacies? What do I mean by that? Well, what experiments tell us, individual simple experiments tell us, are correlations. Okay? So for instance, I know that I gave a bunch of people a certain drug and they all got cancer. So I know there's a correlation between this drug and getting cancer. Or let's say this drug and not getting cancer, or whatever. But the experiment tells you that there's a correlation. But what we want is causal information. I want to know, does this drug cause cancer, or does this drug prevent cancer? Okay. I don't want to just know correlational data. I want to know causal things. But all experiments tell us, for the most part, I'll get to this later, but is correlational data. Okay, we want to know if A prevents cancer. But so we want to know a causal claim, but what are we given by the experiment? Some people ingested A, some didn't. The people who ingested A didn't get cancer. The ones who don't ingest A did get cancer. So all we know is this correlation. How can we move from a correlation non-fallaciously to a causal claim? Or can we? If what I've said about false cause is right, does that mean that science and the drug industry and every other kind of scientific enterprise based on experiments is fallacious? Well, no, but it's instructive to see why it's not fallacious. And the reason it's not fallacious is because when it's done well, it's not committing the false cause fallacy. Now, suppose that there is a correlation between A and B. Okay, and we know this from an experiment, let's say, or we might know it from the cheerleaders' ribbons, or we might know it from looking at records of football games and when a team won and how many times different people carried the ball. So let's suppose that there really is a correlation. We're not doubting that between A and B. How could we explain that correlation? Well, it turns out there's 4 ways to explain why A and B could be correlated, if they are. And here they are. It could just be coincidence. Yeah, there's a correlation, but, sometimes there are coincidences. Okay? So that's one possible explanation. It could be that A causes B. Okay, if A and B are correlated, maybe the explanation is that A causes B. How does that explain the correlation? Well, because A happens, it causes B, and now you've got A and B together, because A happened and then B happened, and now they're correlated. Here's another explanation. B causes A. B happens, it causes A, and now you've got A and B together. A fourth possibility is that there's a common cause. Okay, there's something C, some other thing, that causes both A and B. So A isn't causing B, B isn't causing A. But there is some other thing that's causing both of them. How does that explain the correlation? Well, because C happens, it causes A and B, and now you've got A and B together. Okay? Given that there's these 4 possible explanations for a correlation, and given that what we want to establish, let's say, what we're interested in showing, is that A causes B, how can we show that? How can we show that A causes B if what we have is a correlation and there's 4 possible explanations, 3 of which are different from A causes B? Well, in the simplest terms, what you do is you rule the other 3 out somehow. That's how, and if you can rule the other 3 out, either completely rule them out or give a good argument to show that they're unlikely, because these are usually inductive arguments. So we're looking for inductive strength rather than deductive validity. But you show that these other things are really implausible or really not very likely. then to that extent, you've shown that this is the best explanation. How do we rule these other things out? Well, how do we rule out coincidence? Usually statistics. Okay, so let's look at this example. During the past 2 months, every time the cheerleaders have worn blue ribbons, the basketball teams won. If we want to keep winning, we better continue to wear the blue ribbons. Well, what you would want to do is collect data on more games, right? So, suppose you've got 8 games and 4 they wore blue ribbons, 4 they wore red. Every time they wore blue, they won. Every time they wore red, they lost. You can do stats on that and figure out how likely is it that that was just coincidence. But once it gets, let's say you're interested in this and you do 100 games, 50 with blue, 50 with red, and they win all 50 where the cheerleader's wearing blue, and they lose all 50. At that point, coincidence starts to look really unlikely. Okay. Now, how much data do you need to collect? How are the ways you could collect it? I don't want to get into that. There are courses on that. You do stats on that as part of, if you're a science major, that's one of the things you would do. But the short answer is you try to rule out coincidence by collecting enough data to rule it out. Or if not rule it out, generally you can't 100% rule it out. You collect enough data so that the probability that it's coincidence is really small. And what counts as really small depends on the context. Okay. How do you rule out B causes A? I'm going to say something right now about ruling that out, but I want to say one quick thing. Sometimes you can tell at least the difference between 2 and 3 just by temporal order. If A always happens before B, that's one way to rule out that B is causing A. Okay, so if, just to go back to the Taco Bell example, if, it's always the case that I'm getting sick 6 hours after eating Taco Bell, then it's probably not the case that getting sick is causing me to eat Taco Bell, right? There's no backwards causation. I'll get to that later, but for now, how might you rule out B causing A in general? Well, one way, it's not the only way. You could also try to use temporal factors. But one way is you intervene with B. You just implement B and see if A results. Okay. You could do this in the Taco Bell case too, actually. So for instance, sorry, let's go back to this example, the football case. Every time Marshawn Lynch carries more than 30 times, the Seahawks win. So all Carroll has to do to keep them winning is give the ball to Lynch 30 times a game. What's really going on here, by the way, is that there is this correlation, but it's not because A is causing B, it's because B is causing A. What do I mean by that? Is it the case that giving this player, the running back, a lot of carries is causing the team to win, the team to have a higher score than its opponent? Or is it the case that when a team has a big lead, that causes that team to run the ball more, to give it to their running back more as opposed to passing the ball? Well, the second one is really the case. B is causing A here. By the way, this doesn't matter. Don't worry about why this is true. But if you're curious, it's when a team is ahead, you want to run the clock out. You want to make the game over, because if the more time there is, the more time your opponent has to score points and possibly win. So if you're already winning, you want to end the game. And running the ball takes more time off the clock than passing the ball on average. So that's why when teams are already in a position where they're going to win, that makes them run the ball more, because they're trying to end the game quickly by running out the clock. Passing the ball doesn't take as much time off the clock. Okay. But how could you tell? Suppose you didn't know enough about football to realize that it's really B causing A, just based on your knowledge. Well, one way you could find out is you could just run an experiment where you just give, you have a bunch of games, you give one team a big lead and see if that makes them run the ball more. And sure enough, spoiler alert, that'll happen, right? If you give a team a lead, they're going to start running the ball more because they want to end the game so that they'll win. Okay. So that's what I mean by you intervene with B and see if A results. You give the team a big lead and see if that results in them running the ball more. And in this case, they will. And that would be a way you could say, oh, maybe it isn't A causing B, maybe it's B causing A. So you could rule out this if that didn't happen. Right? If you gave them a big lead, but they didn't run the ball anymore, then maybe that's one way of ruling out B causes A. Here's another example of the same thing. Studies show that people located in emergency rooms have a 5,000% greater chance of dying within a week than people located elsewhere. I just made that particular stat up, but essentially it's right, of course, right? People in an emergency room are much more likely to be dead within a week than people just randomly located anywhere, right? So that correlation holds. But the person making this argument says, so if you want someone to disappear, if you want to kill someone, just take them to an emergency room. Well, here they're assuming that it's just being located at an emergency room that's causing the high death rate, the mortality rate. But maybe it's the other way around, right? Maybe it's already being such that you're probably going to die is why someone goes to the emergency room, right? How could you test that? Well, you make people super sick and see if that induces them to relocate to an emergency room, and it will, right? So that's one way to see if it is B causing A. Here's the trickiest one. How do you rule out a common cause? Or how do you approach that? Remember, we want to establish A causes B. How do we rule out a common cause? Well, you do that by having a control group that is the same as your experimental group in terms of everything you can think of, anything you think that could plausibly be causally involved. It's the same in every respect, except for whether or not A is present. So if there is a common cause, that thing is going to be present in both groups. Okay, so that's how you try to rule out a common cause. So let's walk through an example. And I'm going to walk through a very quick explanation of why there's double-blind placebo controls in drug studies, sometimes triple-blind, but why you have first placebo studies and then why you have double-blind placebo. So here's the situation. A patient gets sick, goes to a doctor, they get a drug, and they feel better. Okay, so now we've got a correlation between the drug and feeling better, right? And suppose this happens a lot. You've got a lot of people who go to the doctor, they get a certain kind of medication, and then they feel better afterwards. Okay? Now you might think, oh, well, then the drug's making them feel better. Well, not necessarily. Okay, there could be a lot of other things going on. What are some other factors? What are some other things that happened with these patients besides just getting this drug? Well, here's a few. They talked to a doctor. They got some medication. Because they got medication, they were hopeful about a cure, or they were expecting to feel better. Okay, those also happened. They also did get a medication that they took, right? So there's a list of things that happened besides just getting the medication. Okay. Now, maybe the trip to the doctor was a common cause, so to speak, of getting the medication and feeling better. So it's not that the medication caused the person to feel better. It's that the person took a trip to the doctor and spoke to the doctor, and then that had two effects. One is the person got medication. The medication didn't do anything, let's say. Could be a sugar pill, right? But the trip to the doctor caused that to happen. It also caused something else. It caused them to expect to feel better. So maybe there's a common cause, right? This is called the placebo effect, by the way. It's where people who actually don't get any medication report feeling better afterwards. And that's because they expect. So the problem is then how can you tell if the drug really is having an effect, if there's a placebo effect, possibly? How can you tell that a medication works? Well, this is where you have a control group, right? This isn't double blind yet. This is still single blind. Single blind meaning just the patient doesn't know. Okay. So you have two groups. There's group A that goes to the doctor, gets the drug, your experimental group, and then you have a control group. They go to the doctor, et cetera, but they just get a sugar pill. They get a placebo. But you try to make everything else the same. They're still going to a doctor. So these people are still going to expect to get better. You don't tell them that it's just a sugar pill. You tell everybody, okay, that they're getting the drug. And why do you do that? Well, because now, if it was just them expecting to feel better, then both groups should improve because both groups are expecting to feel better, okay? So if both groups improve, then you know that whatever caused the improvement was something applicable to both groups. So it wasn't the drug, because only one group got the drug, but both groups felt better. Okay? So it couldn't have been the drug, it must have been something else, probably placebo effect, right? It was something about them, the trip to the doctor, or them expecting to feel better or to improve somehow, or the hopefulness. If only group A improves, then maybe it was the drug. So suppose you do this, but then only this group gets better, this group doesn't. But they both expected to feel better, but really, even though they both expected to feel better, only the group that got the drug really improved. Now that's some reason to think maybe it really was the drug, okay? So you've ruled out the common cause, let's say, or at least you think you have. This is why we go to double blind. But you think you've ruled out this common cause of expecting to feel better. Well, you haven't really. Why do you go double blind for these kinds of studies? Well, let's suppose the doctor knows which pills are real and which are fake. So the doctor is part of the study. They have 100 patients. 50 of them are getting the real medication. 50 of them are getting placebo. They don't tell the patients which is which. So all of the patients, let's say, feel hopeful. And if all of them improve, then you know it's not the drug. If only the ones who got the drug improve, but the group who got placebo don't, then you know it wasn't them feeling hopeful necessarily. It was the drug. Okay? That's the thinking. But here's why science is hard. Maybe there really still is a common cause that you just haven't figured out yet. Maybe, and this in fact happened a lot, so it was a problem with a lot of medications in the early days of drug studies. The medication really isn't working. There really was another common cause that hadn't been appropriately recognized. If the doctor knows which pills are real and which are fake, then she might be more enthusiastic in discussion with the patients who get the drug, right? The doctor, when talking with a patient that's getting the real drug, is like, okay, you really only take this in the morning and really only take it at night, and, gives them much better instructions. And if the doctor knows that it's just a placebo, it's a sugar pill, maybe the doctor, even if they're trying to do a good job, no one's the best actor in the world, right? So, well, I guess one person would be the best actor in the world. Whatever, forget. Anyway, even if the doctor's trying, the doctor might, just be a little bit less enthusiastic with the sugar. Well, okay, here's a couple pills, take 2 a day, give me a call, right? And so maybe the patients who get the real drug really are a little more hopeful because their doctor was more enthusiastic. And the ones who got placebo aren't quite as enthusiastic because the doctor kind of blew them off a little bit more. Now that might sound like not a big effect, but it can be a huge effect, actually. It's a problem in a lot of early studies. That's why, you would move to double blind. Not only does the patient not know, but the person giving the patients the drugs doesn't know. So now you're controlling for that as well. So now in Group A, here are the things that are going on with the Group A people. They went to a doctor, they got a drug, the doctor knew they were getting the drug. This isn't double blind yet, this is single blind. But with Group B, went to a doctor, got placebo, the doctor knew they were getting placebo. Okay, so suppose you didn't make the doctor blind, the doctor knows. Well, if Group A improves, but Group B doesn't, the explanation could be any of the different factors. It might be the difference between drug and placebo, but it could also be that the difference between the person giving them their medication knew it was a drug versus knew it was a placebo. Maybe that actually is the difference somehow. So now we have to control for that. How do you control for that? You make both groups the same in this respect. Okay? Meaning the test and the test group and control group should be the same in terms of the doctor's beliefs about whether they're getting the actual drug. And so the way you do it, now both groups go to a doctor. Okay, both go to a doctor. And in both groups, the doctor doesn't know if they're getting the drug. So the doctor's just given 100 bottles of pills that are randomized, and is told to give these to patients. Now they keep tabs on them. Each pill has or bottle has a number on it. So the doctor can tell the people, okay, I gave Smith bottle number 1, I gave Jones bottle number 2, I gave Jackson bottle number 3, but it's random whether any of those bottles had placebo or actual drug. So the doctor doesn't know. So presumably the doctor will interact with the patients the same way from both groups. Well, now, if Group A improves but Group B doesn't, you have reason to think that it's not the doctor isn't a common cause and the doctor's knowledge isn't a common cause. It's really got to be the drug versus placebo. So anyway, this is just a long way of saying that the way to rule out a common cause is usually pretty difficult. It involves control groups and trying to figure out how to make everything the same in both groups except for one factor. That's how you would rule out there being a common cause. So let's summarize. False cause fallacy, or the most basic form of it, is this. A and B are correlated, therefore A causes B. And that is just fallacious. You shouldn't do that. That's a bad argument. Non-fallacious causal inference would be this. A and B are correlated. So you've got the same premise as before, but you do 3 more things. You give some reason to think that the other 3 explanations are unlikely. It's not coincidence, or probably not coincidence, probably isn't B causing A, and probably no common cause. And if you can, to the extent you rule these out or make them seem implausible, then you can not validly infer, but strongly infer, because these are inductive arguments. You can have a strong argument to the effect that it's A causing B. Okay? So that's good. That's the best. What about this? I want to pick up on something I said earlier about the most basic version, which was this. A and B are correlated, therefore A causes B. This is the best version. They're correlated and you've ruled the other 3 out. But what about something like this? I ate old shrimp this morning and this afternoon I'm sick, therefore the shrimp made me sick. Well, the order of events does rule out B causing A. So it's not just this, correlation, therefore A causes B, because there is some reason to think B isn't causing A. The time difference. Okay, the sickness can't go back in time and make me eat shrimp. So the point is that this is still a bad argument, probably, but it's better than this. So causal arguments are generally inductive arguments. This is inductively weak. To the extent that you get closer to this, you become inductively more strong. Okay? So what I want to claim now, the point I want to make now, is that this is a false cause fallacy. Just from correlation to causation, that's false cause. And this is usually, in fact, the definition that I gave at the beginning sort of focused on this example. But even something like this is still false cause, as long as you haven't ruled out the other three possibilities. You're still making a bad causal inference. This might be a little bit inductively stronger than this, right? So they're both weak. This is weaker than that because there's still two other explanations that haven't been addressed. So we can't just go to this. But it's still false cause. Okay. All right. Let's see some real world examples here. Does it pay to be a flirt? By the way, this is a news report on a scientific study. And usually news reports on scientific studies leave some things out. I'm going to get back to that in a minute. For now, just realize that I'm going to talk about what's expressed in the news report as though that's everything. But I'll return to that point in a minute. Flirting at the office is not only taboo, but it could even take a toll on your financial future. Women who cross their legs provocatively, wear short skirts, or massage a man's shoulders at work get fewer pay raises and promotions, according to USA Today. Well, this is actually a report on a scientific study. Okay, so the actual study was at Tulane University, and according to this study, there's a certain correlation. Certain kinds of behaviors are correlated with certain kinds of career events, like how many raises and promotions you get. So the study said 49% of female MBA graduates polled admitted that they had tried to advance their careers by sometimes engaging in certain sexual behaviors, including flirty emails, wearing revealing clothing. Respondents who said they never engaged in such activity, so here we're going to be getting the correlation information. So you've got two groups. You've got the group that said they never engaged in that kind of activity, and the group of people who said they did engage in that activity. And in the first group, they earned an average of 3 promotions. The second group earned 2 on average. The first group earned between $75K and $100K, and the second group earned between $50 and $75K. So here we see this correlation between certain kinds of social behaviors and certain kinds of career milestones or achievements or something like that. Okay. Tulane professor Arthur Brief said the study suggests that women should be careful about letting men open doors and lift boxes because it's benevolent sexism. We argue that there are negative consequences for women who use sexuality in the workplace. This is a causal claim. It's saying that if women do this, it will cause negative consequences. It will cause fewer promotions and lower income. Okay. And then finally, it says 164 women in the study range from mid-20s to 60. That's a lot of people to interview, so it's probably not correlation. Or it's probably not coincidence. Okay. But notice that, at least given the information we have here, 2 other explanations haven't been ruled out. Okay. So we have a correlation between A and B, social behaviors, sexual behaviors, and career advancement. The assumption is that the behaviors are causing the career advancement effects, either positive or negative. But the only thing that's been ruled out is coincidence. What hasn't been ruled out? Well, one thing that hasn't been ruled out is B causing A. Maybe the amount of money and the career advancing is having an impact on whether people decide to engage in certain kinds of behaviors. So for instance, if you're a woman and you're already making a lot of money and getting promoted, you don't feel any pressure to try to do other things to advance your career, right? Whereas if you're making crap money and you're not getting promoted, there's a sort of subtle pressure to do things you might not otherwise do. Okay, so it could be B causing A. It could also be a common cause, right? So it might be that there's a certain personality type, and that personality type both results in less certain kinds of behavior, but then also completely independently of that causes more someone to do better in their career in one way or another. Now, who really knows what's going on here? But the point is that the only thing that even looks like it's been marginally addressed, as far as we know, is coincidence. 164 is a lot of people, probably not coincidence. One thing I want to say, and this is really important, is if you're really interested in something like this, or you see a news report about a study that says there's some causal connection, it's always a good idea to try to look up the original study, because sometimes the original study is different from the report on it. And one way it can be different is it might be that the original study actually did address common cause or B causing A somehow and ruled them out, maybe. But that just didn't make it into this news report. Okay, that's possible. What I'm saying is that just based on what's in this news report, it looks like a false cause because the other two possibilities haven't been ruled out. This is from The Onion. It's kind of it's a joke, but it gets at common cause as a possible explanation. A decade-long study tracking adults' fitness habits found that those who played racket sports like tennis, badminton, or squash were 47% less likely to die during the study. What do you think? And of course, the headline is "Tennis Leads to Longer Life," as though playing tennis can cause you to live longer. And the first answer is, I knew there was a correlation between paying $400 a week for tennis lessons and having quality medical care. So this is pointing out that, well, maybe there's a common cause. Maybe it's tennis not causing longer life. Maybe there's a common cause. There's something that both causes this group of people to play tennis and causes them to live longer, namely being rich. If you're rich, you can afford to play tennis. But if you're rich, you also get better health care and etc. This is also false cause is a really dangerous issue for internet memes. So things like this. First off, keep in mind, another way an argument can go south is by having false premises. So if this is on the internet, you can't even assume that the correlation it's talking about is actually correct. But even if this is correct, that there are these correlations, it says it's not like it's a pattern or anything. Clearly, it's saying there's a causal connection here. It could be coincidence. It could be B causing A. There could be a common cause. There's an interesting website, and there's I don't know if this is still up, but it's really interesting. And this, I think she was a grad student somewhere, but she got this program that just found huge numbers of correlations in all kinds of data. And it turns out there's an amazing amount of correlation between things. And so this is a correlation between 2000 and 2009. And you can see it's like really tight here. Like that's pretty impressive. And the blue line is the divorce rate in Maine per 1,000 people. And the red line is the per capita consumption of margarine. The lesson here is that correlations can happen all over the place without necessarily there being any causal link. I mean, maybe there's a causal link here. Final joke. I used to think correlation implied causation. Then I took a logic class. Now I don't. Sounds like the class helped. Well, maybe. Get it? Okay, anyway. That's it. That's the last fallacy. The next video, I'm going to talk more about how to do in-depth analysis of passages that contain fallacies. Study hard, do a lot of exercises, and good luck.